Welcome to this eLearn Security video training lesson on HTML5. Today, we will see some of the features introduced by HTML5. We will first focus on the cross-origin resource sharing, and then we will see how the cross-Windows messaging works. CORS is a mechanism that enables client-side cross-origin requests. By using this feature, a browser and a server can communicate, bypassing the same origin policy. This behavior must follow some rules. We can study how CORS works with a few examples. For this video, we will work on two different websites, site.a.site and site.b.site. We will also need to wear the developer's hat. So we previously opened a secure shell connection to the web server hosting site.b.site. To study the web applications, we will use a browser and Burp Suite. So we open the web browser at the following URL, site.a.site. This page can retrieve different resources via XML HTTP requests and display them in the box at the bottom of the page. Users just have to select the resource they want by using the drop-down menu, and then they can click the Get Content button. Let's inspect the source code to understand how the logic works. The HTML form contains three objects: a combo box, the Get Content button, and the Reset button. By using the Select box, we can choose three different resources hosted by siteb.com. Then, the selected resource is used by the Retrieve JavaScript function to perform a cross-domain request. If we take a look at the function, we can see that the target variable contains the currently selected value in the drop-down menu. Target is then used to perform an asynchronous GET request. Finally, the request result is put into the external content div. Let's test it in action by requesting the NoCORS resource. We select it with the drop-down box, and then click the Get Content button. The external content div is still empty. This happens because site.a.site and site.b.site don't share the same origin. Hence, the content of the retrieved document should not be displayed. We switch to the terminal with the SSH session on site.b.site to take a look at nocors.php. It doesn't contain anything special. It's just a single line of text. So, what happens under the browser hood when we click on the Get Content button? We can see that by opening the console. As you can see, the browser already logged that the previous cross-origin request has been blocked. Moreover, the number of blocked actions increments every time that we click the Get Content button. To get an even deeper understanding of this fact, we can intercept the HTTP requests and the responses using Burp Suite. We have already configured our browser to work with Burp, so we will just turn the master interception on and launch our XML HTTP request by clicking on the Get Content button. Burp has intercepted our request to siteb.site/nocors.php. Here we can see the referrer and origin headers. The request starts from the site.a.site origin and lands on the site.b.site origin. This means that, according to the same origin policy, the request is sent. But the JavaScript code performing the request will not be able to read the response. Indeed, if we forward the request, we get the response back. This proves that the request is indeed successful. As you can see, forwarding the response does not sort any change on the page output. This simply increments the number of cross-origin requests blocked by the browser. Now it is time to test a request to a CORS-enabled resource. We disable Burp Master Interception, select the CORS-enabled resource, and click the button. This time, we will request another page named cors.php. Please note that the page is hosted on the same domain as the previous one. The request works! What's the difference between this last request response run and the previous one to the nocores.php page. The code performing the request is the same, and the target domain is the same. To find the answer, we have to take a look at the source of the cores.php page. As we can see, the code within the page sets the header, access control allow origin, to site a.site. This lets a piece of JavaScript code hosted on site A to read the page content. We can now inspect the communication with burp in order to see what has changed under the Web Application Protocol point of view. First, let's go back to burp to activate the master interception. Then we click the Get Content button. The request is almost the same as the previous example. The only thing that has changed is the requested resource. Let's click Forward and wait for the response. As we expected, the response contains the header access control allow origin, and it's set to site a.site. Thanks to this header, we are able to get the content of the page through JavaScript. So as we have seen, this option can be very useful because it allows scripts to read content from a different origin, bypassing the same origin policy. As you can imagine, this feature can be very helpful while programming web applications, but it also raises many security concerns. Indeed, if this header is not properly configured, attackers can steal all the information contained in the target domain by letting the victim visit a crafted website under their control. We said properly configured because the header can be set to allow any domain by using an asterisk as its value. If the header is set like this, any site on the internet can read a resource content. In most cases, developers should restrict the domains that can access a specific resource by setting the access control allow origin header. Moreover, the standard and real-world implementations prohibit the use of the access control allow origin asterisk and the access control allow credentials headers together. It would actually be a very insecure configuration. Anyway, this doesn't stop developers from implementing a workaround to get the same result. Let's switch to the terminal to see the content of the dyncores.php file. This file dynamically constructs the access control allow origin header by using the actual request origin. Please ignore the web page form. We will get back to that later. Let's switch to the browser to understand the security implications of this unfortunate development choice. We select the Dynamic Cores Enabled resource and click the Get Content button. The request has nothing special, so we can forward it. Also, the response seems legit. It has 2 cores headers enabled. Let's switch to the HTTP History tab and forward the previous request to the repeater to do some tests on the origin header. As we have just seen, if we forward the request as is, we get a response back. But if we change the request origin header to something else like hacker.site, the response will contain hacker.site in the allow origin header. This means that any site on the internet will be able to send authenticated requests to siteb.site/dyncores.php and read the response. The configuration introduces a cross-site request forgery vulnerability by design. What does this mean in practice? We can see that by taking a look at the remainder of the dyncores.php. dyncores.php contains a web form with a very strong anti-cross-site request forgery token. We can verify this by disabling the master interception. Switching to the web browser, and click the Get Content button a couple of times. As you can see, every token is different from the previous one. This should protect the form from CSRF requests. As we've seen, unfortunately, this resource is accessible via JavaScript from any site on the internet, thus letting an attacker submit the form with a simple AJAX request. Looking at the source of the page, we can see that it contains a form which asks for some data and submits that data plus the anti-CSRF token to process.php. Process.php stores the data and displays how many values have been stored. If we call it directly, it just displays how many values have been stored. We cannot submit any data without using a new token. Now, we have just seen that dyncores.php accepts CORS requests from any source. This means that we can create a script on a site under our control and post some data on behalf of Site B legitimate users. We wrote an HTML page on our hacker site. Via AJAX, this page loads the content of siteb.site/dynscores.php. Sets a value for the input text box, and then submits it. If we open hacker.site/test.html, we actually post the form on siteb.site. This attack could also be scripted to automate it. For example, in brute.html, we created a script that generates iframes that load test.html, hides them from the users, and includes them in the current page. The script is configured to generate and load 50 iframes. This means that it's configured to submit 50 times the form on Site B. If we open siteb.site/process.php, we can see the actual number of submitted values. Now, we can open hacker.site/brute.html, wait for the page to load, and check that the number of submitted values increased by 50. Think about the risks that this could pose to a home banking site, or to any other site hosting sensitive transactions. The next HTML5 feature we're going to see is cross-Windows messaging. This HTML5 feature allows iframes, pop-ups, and the current windows to communicate with each other. The necessary condition for this mechanism to work is that the two communicating windows must have some kind of relationship. For example, a window can exchange information with an included iframe, or it can communicate with another window opened as a pop-up. Let's see how it works with an example. Our target web application is hosted at the address sitea.site/crosswm. The code of this page simply includes an iframe that is hosted on a different domain. In this case, it is hosted at the domain siteb.site. And the requested resource is /crosswindow/index.html. Let's now take a look at the JavaScript function called by the send button. As we can see, it creates a variable that points to the iframe. And then it sends a message to it. Now that we know the sender source code, let's inspect the receiver source code. Here, we print our current domain. So this will print siteb.site. Then in the following JavaScript piece of code, we add an event listener and we define the function receiveMessage. The code waits for incoming messages. It first verifies if the origin domain is another.site. If this condition evaluates to false, it will print the message not allowed. Otherwise, it will continue with the code and will print the received message. Now that we know the code of both sender and receiver, let's go back in the web app and see what happens. Note that the request originates from the domain site.a.site, and that the receiver will accept messages only from the domain another.site. This means that we shouldn't be able to send the message. Let's then insert a message and click the button. As we can see, the message "not allowed" is printed. This happens because the check in the receiver source code evaluates to false. A typical security issue happens when the receiver window does not check the origin of the sender. With this bad configuration, the receiver windows could interact with any sender, regardless if it is trusted or not. Let's see this case in action. Let's go back in the receiver source code and let's delete the control from the origin domain. We can save the file and then go back to the web page. If this works, we should see our message inside the iframe. So we can click again the Send button, and the message is included in the iframe. As you can imagine, without the right controls, this feature can lead to security issues as it could give access to the page content to external entities. In this video, we've seen two features introduced by HTML5 and the potential security risks that rise if developers don't enforce a whitelist of allowed origins. And this concludes our video lesson. Thanks very much for joining us.